In this recording, we will explore the future value of constant growth annuities. These type of calculations are particularly pertinent in inflationary environments. We will illustrate the concept through an example. So let's present the example first, and then we will explore the conceptual foundations of this particular context. Let's assume that there's a young couple who had their first baby, and they wish to save for their child's college education, and they would like to make sure that they have enough funds available for her education at the time she starts college. So they decide to make deposits into an educational savings account on each of their daughter's birthdays, starting with her first birthday. So first savings is going to be deposited into her account on her first birthday. Let's assume that the educational savings account will return a constant 10% return, or will return a constant 10%. The parents deposit $2,000 on their daughter's first birthday and plan to increase the size of their deposit by 3% each year. It is clear that this increase is intended to preserve the constant or the real value of their deposit. So technically we could assume that they are saving in a 3% inflationary environment. So their increasing savings will ensure that they are in real terms depositing $2,000 starting from their first year. So assuming that the parents have already made the deposit for their daughter's first birthday, we will calculate the amount that is available for their daughter's college expenses on her 18th birthday. So practically we are asking, what is the accumulation as of child's 18th birthday? Let's take a look at this problem as an annuity. So if you assume that each deposit starting from an amount of A grows at a rate of G%, the future value of annuity can be constructed as initial deposit, which will take place at the end of the first birthday or at the end of the first year, and this deposit is going to be compounded n-1 times, and then the second deposit is going to grow at a rate of G%. So the second deposit is going to be A times 1 plus G, and this deposit is going to be compounded by n-2 times. Third deposit similarly is going to be A times 1 plus G to the power 2. This is the third deposit, and this deposit is going to be compounded by n-3 times, and so on. So the last deposit that is not going to be compounded at all is going to be A times 1 plus G to the power n-1. So the first deposit compounds n-1 times, second one n-2 times, and the last deposit not at all. So the compounding declines, and then eventually there's zero compounding. Now, similar to the previous future value of an annuity derivation, we are going to multiply future value growth annuity with 1 plus I divided by 1 plus G. So left-hand side and right-hand side, both sides are multiplied with the same quantity, which does not change the equation. So we essentially obtain another equation. This second equation, since interest rates are assumed to be larger than the growth rate of the annuities, is going to be larger than the previous equation that we demonstrated in 1, or exhibited in equation 1. So we are going to again subtract this small sum in equation 1 from the sum we get in equation 2 and solve the equation for future value of growth annuity. So if we rearrange the terms in here, the left hand side has this the equation 2, left hand side of the equation 2, and this is the left hand side of the equation 1. This is the difference. And when we consider all the terms in both equations, only 2 terms survive in here. In equation 2, a times 1 plus I to the power n divided by 1 plus g, and in equation 2, only a times 1 plus g to the n minus 1. All other terms cancel out. Now we rearrange the left-hand side as future value of growth annuity, and then inside the parentheses we have 1 plus I divided by 1 plus g minus 1. And on the right-hand side we have a 1 plus I to the power n 1 plus g minus a 1 plus g to the power n minus 1. So arranging the left-hand side, we get I minus g over 1 plus g times future value of growth annuity. Arranging the right-hand side, we get 1 plus I to the power n divided by 1 plus g, and on the right-hand side, we have 1 plus g to the power n divided by 1 plus g. As you see in here, denominators are the same. So on the nominator, we have 1 plus I to the power n minus 1 plus g to the power n. Denominator is 1 plus g. And solving this for future value of growth annuity produces a times 1 plus I to the power n minus 1 plus g to the power n divided by I minus g. So 1 minus g's here cancel out, and then I minus g in here comes to the denominator, and we have the future value of growth annuity formula. So provided that an annuity deposited grows at a rate of g, future value of that annuity at the end of the year n is given by this formula. So this is very much what we are looking for in the previous example. So we will start to deposit $2,000 in the first birthday of the child, and then these deposits are going to grow at a rate of g, and we would like to know by the end of her 18th birthday how much money we accumulated. And interest rate obviously is I. The interest that the account earns is 10%, so we're going to use 10% in here. Our annuity is going to grow at a rate of 3%, and we are looking for the amount that is going to be accumulated at the end of the year n. So if you plug in the figures in here, the future value growth annuity, the initial amount that we're going to deposit is $2,000, which is the first deposit that takes place in year 1, and other figures 10% and 3%, and we are looking for the accumulated value 18 years from now, or at the end of the 18th year, and that turns out to be $110,213.83. So if they every year, if they save $2,000 and increase this deposit by 3% per year, by the end of her 18th birthday, they will accumulate $110,213.83. Well, we can argue whether this is at all possible or not, or will help her just to complete her college education, but this is the amount that is going to be available at the end of her 18th birthday. So this is a simple future value of growth annuity calculation. We derived the formula, implemented the formula in the context of this equation. Let's take a look at another approach to do the same calculation. We could use real interest rates to calculate the future value of growth annuity. In this case, we could start with the real interest rates, where real interest rate can be calculated as 1 plus nominal interest rate divided by 1 plus inflation rate minus 1. This means that real interest rate is 6.796%. Once we calculate the real interest rate, we will plug that in the standard future value annuity formula. Instead of nominal interest rate, however, we are going to use real interest rate that we derived in here. So A, which is the initial deposit, is going to be here, and then real interest rate of 6.796, number of years n minus 1 divided by, again, 0.7694, and this will produce $66,681.18. Now, this is not the same figure that we calculated in the previous example where we used the formula, because this future value is calculated in real terms or year one dollar terms. So now we need to compound this and bring this up to year $18. So since there is 3% inflation, we will take this amount, which is the dollar amount as of year one, compound it 17 years to obtain the year 18 value of the accumulated sum. So we could again execute the same, or calculate the same end of year future value of growth annuity by utilizing real interest rates, but the amount that we calculate as standard future value is indeed in terms of year $1, and then that would require one set of interventions to bring the year $1 to the year $18. So here we take the year $1 and then compound it 17 times to 110,213.83. So whichever is more convenient for you or clear for you, you could utilize either approach. Now we are going to look at a present value of constant growth annuity problem. So we, in the previous example, we explored the future value of constant growth annuity. Now we are going to use an example that requires us to look at the present value of constant growth annuity. So here is the example. Your mother now has $1 million invested in an account that pays 6% nominal interest rate. She expects inflation to be on average about 3%, and she wants to make annual constant dollar or real end of year withdrawals over each of the next 20 years, and she would like to draw down the savings balance to zero at the end of the 20th year. So the question is, how large should be her initial withdrawal? And then, of course, we can calculate the subsequent withdrawals, but the key thing is just to figure out the initial withdrawal that is going to grow at a rate of 3%. Her withdrawals will change in nominal terms, but they will remain constant in real terms. This means that in a 3% inflation environment, although her withdrawals are going to grow at a rate of 3%, she will have the purchasing power of the initial withdrawal that she made at the end of the first year. So if you want to preserve, let's say, today's $100 purchasing power in the forthcoming years in a 3% inflation environment, our next withdrawal has to be $103. The following withdrawal has to be $106.09, and so on. So the concept of increasing withdrawals are pertinent to the inflationary environments, and the approach that we are going to demonstrate here will help us to understand and execute calculations under those contexts. So how we can calculate this? Well, since we already derived the equation for future value of growth annuity, we could utilize that future value of constant growth annuity to calculate present value of constant growth annuity. So all we have to do is just take the future value of constant growth annuity and discount it to time 0. In this case, we will use a discount factor and bring this down to time 0 by discounting by using 1 over 1 plus I to the power n. So this is the formula for present value of constant growth annuity. So in our example, we know what is the present value of the constant growth annuity, which is $1 million that the mother has. We don't know what the initial withdrawal is going to be, so this is the annuity that is going to grow at a rate of 3%. So interest rate is the 6% that the account is going to earn. G is the growth rate of the annuity, which is 3%. And we are looking for a 20-year period of withdrawal, so n is equal to 20. And we can execute the calculation and calculate A to find out what's supposed to be the first withdrawal. So if you plug the figures into the equation, A turns out to be $68,674.09. So if the mother withdraws $68,674.09 at the end of the first year, and then grows this amount by 3% going forward over the 20-year period, there's not going to be any money left in the account. Similar to the previous example, we could execute this transaction by using real interest rate. So in this case, again, real interest rate is equal to 1 plus nominal interest rate divided by 1 plus inflation rate minus 1, which in this case is 2.91%. Plug into the standard present value of annuity formula. We calculate the A as $66,673.87. However, this figure is in terms of year $0. So in order to calculate the year 1 withdrawal, we need to grow this by 1 period to year 1. When we do that, we get $67,674.09, which is consistent with the previous explanation or previous solution. So if we use the real interest rates, again, we need another iteration after we calculate the annuity. As of year 0, we need to update to year 1 annuity, which is $68,674.09. So A that we get, let's call it A star, which is the annuity as of year $0, and then the annuity that we are looking for, which is the first withdrawal, which is in terms of year $1, $68,674.09. So this simple example illustrates the constant growth annuity, but in the context of present value. Now there are a few other variations. We can also calculate present value of perpetual cash flows. So there are some type of cash flows that continue to the perpetuity. So how we can calculate the present value of perpetual annuity, that is a constant stream of cash flows that are going to last forever. So present value of constant annual perpetuity is equal to A over interest rate. So the amount divided by interest rate gives us the present value of this perpetuity. And there is a simple proof in here. So simply we construct the model. Again, we are trying to calculate the present value of a infinite stream of $8 that we are going to receive. So $8 that we're going to receive in year one is discounted one period. $8 that we're going to receive in period two is going to be discounted by 1 plus I to the 2 to the power 2, and so on. So this continues to the infinity, and we could simply take this and multiply both sides with 1 plus I, and obviously since I is larger than 0, this equation 2 becomes larger than equation 1. We subtract equation 1 from equation 2 to receive to get present value times 1 plus I minus present value on the left hand side, and all the terms except for A cancel out in these two, and solve this for present value. Simply we get A over I. So this is the present value of perpetuity. If you receive cash flows forever, constant amount of cash flows forever, the present value of these cash flows can be calculated by using simply the amount that we are going to receive divided by interest payments. Are there any financial instruments that comply to this model? Yes, preferred shares, for instance, are typically calculated by using a perpetuity, present value of perpetuity approach. We have two variations of this. These cash flows may grow at a constant rate or may decline at a constant rate. Under those circumstances, we could use constant growth perpetuity, where the value of the constant growth perpetuity is equal to A over I minus G. And in the case of diminishing perpetuities, where every year we receive G% less of the cash flow, or A declines by G%, the present value of diminishing annual perpetuity is equal to A over I plus G. And then the proofs are in here very much similar to the previous cases, so I'm not going to go over the proofs of these two equations. So this wraps up the variations on top of the basic standard annuities. We reviewed the present value of constant growth annuities, future value of constant growth annuities. We presented the present value of perpetuity, and also growing and diminishing perpetuities.